good afternoon. Sorry, everyone. Welcome to this new session of Quantum in Practice. We'll present briefly the organizers, CCFR and TQCI, both parts of TerraTech, and then we'll be ready for this second session with QUOBLY, because we had the first one last week with Marta Brzezinska. And today we'll be with Alain Champenois, who will be also with Nicolas from QUOBLY. So let me just present the organizers. Are TQCI, the TerraTech Quantum Computing Initiative. Its objectives are to develop the ecosystem, to prepare skills, and also to improve the understanding of programming models. So to that purpose, TQCI organizes seminars throughout the year. Agenda and replays are available on the QR code you see on the screen. TQCI also works at consolidating the ecosystem through projects with industrial members, such as this one, Quantum in Practice. The second organizer is CCFR, part of the EuroCC project, and serves as the French NCC among 36 centers in Europe. The objectives are to connect industrials, academics, and public administrations with the right resources, projects, and training opportunities. It's also aimed to map key players so everyone can access the most relevant expertise in HPC, AI, and quantum computing. Our missions revolve around the various actions you see right now on the screen, with the constant goal of supporting you, always free of charge. So let me just highlight a company's support, personalized and tailored to each need. You have examples, have details, and also interviews available now on our website and YouTube channel to give you an overview of what we can offer and how we can help in the use of HPC and AI, whatever the subject is. So please, if you have any question about it, don't hesitate to contact us. But let me also tell you a bit about our trainings, because we organize some summer schools in HPC and quantum computing, and throughout the year we also have access to many webinars, many trainings on various topics and levels. You can find the full list on the website or connect our LinkedIn so you don't miss anything. All the sessions are recorded, such as today, so you can catch up anytime on our YouTube channel. And let me just focus a few seconds about the Grace Card School 2026, which is an HPC summer school. It will start on June 22nd, so almost 2 weeks now. Registrations are still open. You can attend one day, one lecture only, or the full 2 weeks if the program is interested for you. So this brings us to today's webinar. Quantum in Practice is dedicated to exploring tools and real-world applications for you to practice with today's quantum ecosystem. Each session features a leading quantum technology provider, such as today with QUOBLY and last week with QUOBLY. But you will also have replays of the previous ones with Pascal and QPerfect on our YouTube channel. And later you will have also the sessions with IS Plus and IBM, Candela, IQM, and I hope many more. If you have any questions during this webinar, please use the chat. Every question will be answered, of course. And well, now it's time to give the floor to Alain Champenois and Nicolas Descoteaux. I'm sorry, I forgot the last name earlier, but both QUOBLY experts, they are here for you. So please enjoy this webinar and see you later. Bye.
So hello, everyone. I'm going to share my screen like this. I think, Marie, everything's right?
Perfect now. Thank you.
Yes. So good afternoon, everyone. Happy to be here. Thank you for participating to this QUOBLY seminar. I'm going to talk a bit about the history of QUOBLY to start with. So let's start with where QUOBLY stands today in June 2026. So we began in 2022 as a bold spin-off of from CA and CNRS. We take the pointer here. There's a pointer here. So, and we evolved into a deeply international force. So today we are a world-class team of over 100 physicists and engineers representing 18 nationalities, different nationalities, with more than half holding PhDs. We are now, our footprint here is reached from Paris and Taiwan to subsidiaries in Singapore and Canada. And we are backed by an exclusive industrial partnership with STMicroelectronics. And therefore, with all of this, we have assembled the exact talent and ecosystem required to define the limits of quantum computing today. Our FDSOI technology here is protected by 65 patents. So today, as you can see, we are writing a great new chapter for QUOBLY and for the entire quantum industry, because we are now backed by a secure 115 million Series A funding, and we are moving past tech validation and stepping into an industrial execution. As you can see here, our first commercial computer, Alloy Pioneer, will be accessible through the cloud and will be launched later this year. So a few words about HPC integration of our platform, because we have several advantages, features that are particularly interesting to be integrated in data center and HPC center. Once again, when you are talking about integration of quantum computer in an HPC center, you realize that, of course, those ones becomes quickly obsolete at the fast pace that this domain is evolving. And one of our great advantage is really to be able to upgrade your system, thanks to your semiconductor qubits. It is, in fact, you make a global integration and investment in the quantum computer with a limited footprint of 10 square meters. And what is very, very nice is that this footprint, in fact, and also the power consumption remains controlled when you grow in number of logical qubits. This is thanks to our FDSOI technology that allows us, in fact, to manufacture both the control electronics and the qubits on the same die at cryogenic sub-Kelvin temperature. So enough with our technology and QPU presentation, because today, in fact, it's a seminar about quantum algorithm. It's a seminar where we will explore how Quantum Reservoir Computing, or QRC, will natively shatter the scalability bottleneck by treating the natural quantum complexity as a powerful computational resource. So it's really complexity as a resource. This is the major, I would say, title of the seminar. I'd like to, as you will see, quantum reservoir computing is really an exotic paradigm of computation. There are lots of paradigms of computations, and this one is quite nice. It is at the limit of physics, of classical computation, of AI, and quantum at the same time. So the analogy to start with is that is the analogy of the water bucket. Think of a physical reservoir as a bucket of water, and when you inject data stream like throwing pebbles, the surface naturally creates nonlinear ripples that physically encode the history of your inputs, depending on the size, the shape of the pebble, how fast you throw it, etc., which of course represents your input data, whatever they are, financial or physical kind of data, for instance. Then when at the end, after we are using, in fact, an internal network that is here freezed, we will use the readout here to train a simple classical linear regression on the output layer. And this will be sufficient, in fact, to extract incredible information about the problem in order to solve it. So the reservoir is really a physical black box with a fading memory, of course, because when it bounces on the wall of the bucket, it will fade when time passes by. And when we inject this time series into it, we scramble the history. And this, of course, gives a very expressive state. The readout part is where we observe what happens. And this is, of course, exploiting a system that must be a non-linear dynamical system. And this is the condition for which we will, therefore, after that, only read some lightweight information at the end in order to use some basic linear regression and be able to make prediction about our future inputs on how by understanding our system behaves. So the computational power comes from this highly dynamical nonlinear system. So physical reservoir, not quantum, okay? Physical computing is something not new. It started in the year 2000. And as you can see here, it can be implemented across various physical media, from photonics to spintronics. However, shifting to the substrate of quantum system will allow us to tap into a mathematical representation space that classical hardware can never match. So you can see here the historic of scientific paper about reservoir computing, about the reservoir computing paradigm, the one I explained you with the analogy of the bucket of water. And in fact, after a long discussion about a very exotic physical implementation of it, there was a structural foundation of QRC, Quantum Reservoir Computing, that was cemented here by Nakajima and Fuji in 2017. In fact, what's interesting is that they mathematically proved that disordered dynamic act as a universal. Let me switch maybe, yes, from slide. That they mathematically proved that disordered quantum dynamics can act as a universal approximator on nonlinear histories. And critically, that they can be, by measuring simple local observable, that is completely sufficient to extract full computational richness of the system. So quantum reservoir computing in scientific papers is sometimes referred as also a variant which is called quantum extreme learning machines. There were not, I would say, not that many papers on quantum reservoir computing in the last year, but the trend is really with a nice increase. I didn't find the time to draw a schema about the increasing number of paper, but it's definitely the case with in late 2025 and now in 2026. So here is an operational pipeline. So you have the classical input stream into a fixed quantum reservoir. Fixed meaning here that this part is not trained. It can be, as we will see, calibrated, optimized, or whatever, but it's not trained in a machine learning sense. And at the end of the reservoir, here we take a batch of measurement shots to gather expectation value and optimize our final output in order to have this is optimized, in fact, using a classical linear regression. And the number of observable that you have here is far beyond the number of classical qubits. This allowed us to have here the output equation that is that we have here, the number of synthetic observable, that can definitely be in a much higher dimensionality. So we don't, without adding hardware complexity in terms of number of qubits, depending here on our choice of observable, we will be able to have an expressive classical feature vector that's expressive enough, in fact, in order to use a simple linear combination of them in order to predict our output value. So according to the Covers theorem, which we will see together later, this large feature pool that we have as output will provide us a way to have an expressive linear regression. But let's talk first about some industrial application of quantum reservoir computing. In fact, the quantum reservoir computing is particularly suitable to handle nonlinear time series predictions. When we try to predict highly chaotic, for instance, dynamical systems like fluid flows or Lorentz 96 atmospheric models, in fact, the standard classical model like LSTM will collapse due to exploding gradient problem. And our QRC is natively able to overcome this. It overcomes this by exploiting the natural state space kinematics of the Hilbert space. This is, of course, all this concept that we will see together. But once again, I would like for you to have a global overview first on what are the typical problem, the problem that we can address in the first place with good efficiency. So QRC is also nice to handle signals like spoken digit recognition, or to integrate partial differential equation. In fact, the QRC, you can see the QRC as acting as a temporal signal processor in the way it treats the problem. In another kind of target problems that you can address is to consider the QRC also as a soft sensor. If you take a chemical engineering problem, for instance, where you have some hidden variable that you cannot measure directly, in fact, you will try to predict it. You cannot measure it because physically the sensor does not exist, or it's not viable to put it at a particular place in the system. The idea would be to use the QRC as a virtual sensor, because we will be able to reconstruct, in fact, the internal dynamics of the fluid phase by using the other visible or measured variable that we have in hands and that we will feed into our reservoir. QRC is also, even though historically it was really about addressing time series, nonlinear time series, in fact, it is more and more also studied for classification of static data. Here we definitely exploit, of course, the dimensionality and the separability advantage of the Hilbert space. But for this kind of application, QRC is definitely facing, of course, extremely performant classical alternative like XGBoost or random forest classical method. There was I saw some nice scientific paper talking about that for satellite image classification, or also for molecular description classification, where you have the reference here, quite recent one. And those papers were mentioning, in fact, the the fact that even on those static data, the advantage is that if you don't have much training data available, so if you are in a data scarce case, then typically the quantum reservoir computing retain a powerful generalization property. It will still outperform or at least matching classical algorithm like SVM with significantly fewer records of data. So this might be, once again, QRC is still an open research subject, but especially for classification of static data. I'm referring here to SVM because we will definitely take this as a reference method in a comparison with the reservoir. Standard support vector method are definitely very, let's say, a robust classical AI method with a very good results and a very strong mathematical background. So if you're interested to, let me just check if there are no question in the chat. If you are interested in looking for many other application domain where QRC could bring value, typically predicting cloud server workloads, optimizing smart grids, and many more. This is a nice article that you can look at. So let's start with some foundation models and machine learning theory. So of course I choose the analogy of the bucket, and this looks like magic, right? I want you to get rid, of course, of something that you must abandon right away, is the naive myth of throwing completely arbitrary random quantum reservoir at a problem and just expecting a magic answer that it works. In fact, quantum reservoir computing relies on mathematical engineering, on Hamiltonian engineering, and we designed fixed quantum ansatz, so circuits that are structurally isomorphic to the mathematical symmetries and structure of the target problem class. This is the condition for which we will have efficient and scalable quantum reservoir computing when we address, of course, complex problem, not simple problem. And I would say even particularly complex nonlinear dynamical problem. So the idea, of course, of the initial idea of quantum of the reservoir computing is that it was like a new computing paradigm. To be a computing paradigm, it has to be universal. Otherwise, even in 19th centuries, you had already a mechanical system calculating and computing differential equation, right? But just for very specific task tailored to those ones. Here, the multitasking, the capability of quantum reservoir is still there. Okay, we just changed the scale. Once again, we are not throwing a reservoir for any problem. We are designing a reservoir to address some family, some class of problems. When I say class, it's of course in the mathematical way, the underlying mathematical structure. This is the way you need to see those quantum reservoir. So before continuing on the quantum reservoir, I will make some parentheses with generative AI, also a very amazing subject that I'd like to follow. I would like to make just a comparison between the two, because this gave me the ideas on, or at least not ideas, but a parallel on how both are progressing. So in the first place, as you know, when we're talking about generative and large language model, those ones today are based on 10 to the 3 billion parameters. So this is 1,000 billion. So it's 10 to the 12. We are talking about 10,000 or 100,000 gigabytes. This makes them, of course, as you can see on this light blue part, only accessible through HPC, at least for the training part. And here is the also amount of petaflops, the amount of data, training data sets that are required to obtain those models, to train them, to start from a complex basis. This is incredible, right? One of the idea, of course, and today also in terms of cost, mainly cost of energy. As Turmern say, we are moving from electrons to tokens, but the cost of training of such very huge LLMs today is about $300 million. This is the last cost of the Gemini or ChatGPT kind of training. The idea of quantum reservoir is to have a trend that is much less exponential, of course, but still you will see there is a definite parallel between the evolution between both. The fact, because when you see, of course, at the 4 years compared to 4 years ago in 2022 and right now, we have also improved by 3 orders of magnitude the efficiency of the inference to solve some mathematical benchmark, of course, with the same score, of course, okay, to obtain the same score at a different period of time with different models. And so this is 3 orders of magnitude. This comes, by the way, from a very nice paper written by Aschenbrenner from OpenAI that you can find on the internet. And how did they achieve this 100,000 improvement? In fact, how did they improve this? It is not by physical compute. It's not by the hardware. So if you decompose the progress, in fact, it's largely because of algorithmic efficiencies and what they called unhobbling. I'm not going to the details of this, but it is similar to algorithmic efficiencies in the way on how to use the complexity of the initial model. The initial model was to, as you know, 4 years ago, just to predict one word after the other. This is of course past us. We are far from that now. This was only the basis to build upon that lots of reinforcement learning to train on chain of thoughts, scaffolding, and many other features on which we elaborate, in fact, on this initial model. But the cost, and I would say the initial complexity, the big matrix that was initially built, this matrix can be seen as the complexity of a system, of a dynamical system. And they were able to, in fact, improve by 3 orders of magnitude the efficiency of this complexity without any modification to the number of parameters itself, but just by exploiting differently the inherent complexity of those models. And this is what was done typically by the algorithmic efficiencies and unhobbling. And this is why, of course, 4 years after, we are far away from just predicting the probability of a word after the other. So the parallel for me is like we have quantum reservoir, we have quantum reservoir, or even physical reservoir paradigm, which can be, once again, which must be highly nonlinear dynamical system. And we are trying to find a way to exploit them. And the way we will, of course, succeed in this is really by understanding how to design, how to use this complexity, how to use the complexity as computation. First, let's go back to quantum machine learning in the first place, in general. So if you look at an end-to-end quantum machine learning workflow, you have a clear 5 steps. It starts with, of course, the classical data preparation, the circuit encoding, where you encode the data, the quantum state mapping or feature map, the model execution, depending on which quantum machine learning model you want to use, including, of course, QRC, and the measurement output to come back with a classical value. So the concept of quantum embedding is an important one, because it's really to pass from the classical to the quantum world by representing the classical data in quantum states and preserving the inherent relationship and structure of your data. So there are many different choices to do this quantum embedding. And we will have, in fact, different methods to encode your data depending on the nature of your data, and also depending on the machine learning task that you want to use. All of them have their advantage, and of course, this on its own is a research area, active research area. Okay. We're not going into the details of this part today, but you must understand that there is always a trade-off in terms of qubit requirements, cyclic complexity, noise resilience, and applicability to data types, depending on the one you choose. So basis encoding is something that is suitable for binary strings. It uses as many qubits as the data binary length. And you just need a few gates, in fact, operation to prepare the states. In contrast, you have the amplitude encoding also, which is very qubit efficient with a logarithm complexity, but it is also very complex to prepare. It will cost a lot, in fact, to lots of many gates operation to prepare the states. So it has a trade-off on depending on how you want to explore them afterwards. Today, in quantum reservoir computing in particular, but also in quantum machine learning in general, angle encoding, as we will see later, is much more suitable. But since we are talking about this one later, I'm going to stop here. Also to mention, of course, you can also use Hamiltonian-based encoding, especially if you want to treat some physical problem. And you will, of course, obtain typically as a circuit a structure that embeds the structure of the problem is embedded in the entanglement pattern of your circuit. So let's start with the core mathematical justification why this works, why this is useful, in fact, to operate the way we are going to operate in quantum machine learning and in quantum reservoir computing. So the justification rests on the Covers theorem, and the Covers theorem say explicitly that a non-linearly separable data set, like this one, in a low-dimensional space, x1, x2, is likely to become linearly separable, right and left here, when you map through phi of x this input state into a much higher dimensional space that we called the feature space, and this is done to the feature map phi. So this is, if you take, for instance, here, you could maybe think of, I don't know, a square feature map of a square relationship like a parabolic relationship where you can split through a parabol. Here, the black points from the blank point. Okay, and once you are in this high dimensional, you can classify your data. You can split them much more easily, and this will give you an equation of your line, of your plane, or your hyperplane, depending on the dimension we are talking about, and all of these hyperplane, whatever the dimension, can always be represented in this way with an inner product. So the idea is to find a phi that is appropriate in order to be able, once again, to find some pattern in your that you were not able to see in your input space, but that you will able to much more easily see and then separate linearly in this feature space. So we have another theorem that is quite important, and we call it the represented theorem. Here in this feature space, we need, in order to find the hyper, in order to find the hyperplane that separates your data, you need to find this weight vector, which could be, once again, infinite or exponential dimensional space, depending on the phi view that you have chosen. And thanks to this theorem, in fact, this theorem states that here you can have that the optimal weight vector. The weight vector here is optimal when you find the optimal way to split, to classify your data, okay? But this one can always be expressed as a linear combination of the data point xi from your training set after they have been mapped by the feature map phi of xi. And these scalar coefficient, this linear combination of the scalar coefficient of the linear combination are going to be learned during the training. So thanks to this mathematical theorem, when we come back to our the equation of our hyperplane, you will have, thanks to the linearity of the inner product, you will get, in fact, a function, the kernel that we will call the kernel function, which is here the inner product of your feature map, phi of x and phi of x prime. Xi being your coming from your training data set. So what's interesting to see that if you rewrite once again your hyperplane, you see that here this hyperplane in fact will give you typically a minus sign or a plus sign depending on which side of the hyperplane you are standing, or where your data are standing, the new input data point x, okay? And in fact, to make a classification, when you get a new data point x, as you can see, you don't need to compute explicitly the coordinates of the massive feature space phi of x, which can be, if it's infinite or exponential dimensional, that could, of course, induce many computation. So what you need to do instead is evaluate this kernel, what we call here the kernel function, which is a product state, okay? It's a scalar value that you can measure, that you can, we will see, measure in the case of a quantum computer, but that you need to calculate between the new point, the new data point that you have, and the training one, the xi that you have used to find those coefficients. Okay, this is the basic idea of why we, and the mathematical justification why we are using high dimensional space when we want to address regression problem or classification problem. And we use this, what we call dual formulation, in order to simplify the calculation and the computing time. So let's now switch to a chapter where we will mathematically compare quantum SVM to quantum reservoir computing. Quantum SVM is the hybrid quantum equivalent of the classical support vector machine, from classical to quantum kernel. So the classical kernel theory is based also on another important theorem, which is called the Mercer theorem. And this one, in fact, guarantees that you can find a global optimum if the kernel function I just explained you must be a positive semi-definite function and correspond to a valid inner product. When we say a global optimum, it's really like we have this very complex input data, and we really must ensure that we find an optimal hyperplane to split some features between them. And to find this optimal, it's, as you know, in optimization problem, you are guaranteed to find a global optimum if your optimization landscape is convex. Otherwise, you will drop into into not a global minimum but intermediate ones, and never find the optimum. So this is why, once again, also the support vector machine method and theory is so strong. It is because, thanks to all this mathematical background, we are sure that we are really finding the optimal way to split our data and to find the best classification method. And of course, this comes with a cost in terms of complexity resources, because when you measure or calculate your kernel function, okay, and when you have to do this 2 by 2 with all your different training data in order to optimize the SVM cost function and find the parameter just told you about, okay, the parameter that are important, because those ones, the alpha parameter, are the one that will allow you to calculate and classify any new data points, incoming data points that is not on your training set. All of this optimization will be on a complexity of m to the cubic complexity in terms of number of data points or data vectors in your training set. So this is why, of course, SVM is gives extremely good performance, extremely good results. But in order to limit this complexity, we usually work with very highly qualitative, compact, and diversified training set. So there was a lot of also pre-processing, classical pre-processing to make sure that we have a data set that you use for your training that is highly representative of all your data distribution function. But this is not always possible, right? You don't know in advance, depending on the problem, you don't know in advance the probability distribution of your data, depending on the problem. So by moving from, this comes from the classical SVM theory, right? And we are moving into, when we move into the quantum SVM, we are now moving from the kernel function here to state an inner product of quantum states. But typically this kind of inner product is generally, in fact, a quantum number, a complex number. So a complex number is something that you cannot extract in a single shot, in a single physical measurement, because a complex number is based, as you know, by the real part and the imaginary part. So typically these kind of things are done by quantum circuit. We call it Hadamard test circuit. And this is, for instance, the Hadamard test circuit for the imaginary part of a unitary operator. But here, this is something that we will try to avoid, because this will induce two separate circuits It will induce also the use of ancilla qubits. And besides, once again, as you understood here, the SVM has different parts: the build of the kernel function or kernel matrix and the optimization part. And in the quantum SVM, you still have the optimization part, which is hybrid and still being processed on classical CPU. So we will also avoid to have and work with complex number, typically because the optimization part would have to deal with complex cost function, which makes it non-convex and induce a lot of complexity. So the idea is that we will use a kernel function that will square the inner product. But the way we want to, let's say, see this is to make sure that we still comply with all the strong mathematical background of SVM, or the condition that makes kernel function efficient to classify data or to make regressions, linear regression on them. And so the idea is that to show that this is compatible with the mathematical background of the support vector machine, we need to transform, in fact, the complex transition amplitude. The transition amplitude is the initial one here that that gives us the complex number, and we need to transition into a measurable expectation value, okay, in a single shot. For that, we will use, in fact, an expectation value of the projector on the new states. The projector on the new states is something that will give you the right kernel function, the same kernel function that we decided to use, the one that is squared. In fact, when you prepare the system in phi of x and you take the projector on another states phi prime, okay, this is the projector on phi prime, or on another data point, not phi prime, but phi of x prime. When you take the expectation value of this projector, in fact, what you get by the inner product development, you get this inner product, you get the same kernel function squared. And this is what we will, as we said, this is what we take as our kernel function. And so this kernel function corresponds to the expectation value of the projection or the fidelity between the two data points, x and x prime. And this justifies the fact that we can use this kernel function, the square, because this square, in fact, is really a consequence of measuring the expectation value of the projector, and the expectation value of the projector physically corresponds to the transition probability between the two states. Once again, this is what we are looking for. We are comparing two data. So the inner product is there to see if there is an overlap of the two states. Measure in a single expectation value the fidelity of the two states. Are they the same? How comparable are they? And in fact, when we work in, so far we have worked with pure quantum states, but when, of course, we deal with real quantum hardware, the interaction with the environment introduce decoherence, relaxation, operational noise, and the real states, the real quantum states becomes mixed states, typically mathematically described by density matrix. So on real noisy quantum hardware, it becomes inevitably mandatory to work into the density matrix formalism. And here is the density matrix that corresponds to our previous wave function psi of x. And when we calculate, in fact, the kernel function of those density matrix, because we will now operate in our quantum kernel, the quantum kernel that we need to work, quantum support vector machine theory, we will make the inner products of operators, because our density matrix here becomes operator, and the inner product use the Inner-Schmidt inner product between two operators. This is calculated through the trace between those density matrix, and thanks to the cyclicity of the trace, we get the same results. So this is nice because, once again, it means that if we work in the operator space, in fact, we typically have a kernel function that is strictly linear, that is strictly let's say inner product, but in the density matrix space. How are we going to evaluate quantum kernels? So in machine learning tasks like classification or regression, and in quantum machine learning in general, in fact, we have to calculate inner products between data points all the time. And of course, what is nice is that quantum computing is very efficient to make those kind of inner product calculation, even in very high dimensional vector. When you have encoded your data into high dimensional Hilbert space, even with 20 qubits, you have 2 to the 20 amplitude value for your vector. So it's a huge vector, okay? But in quantum circuit, in the quantum space, in the Hilbert space, in fact, when you operate between quantum states, these operations are not done component-wise. They are done globally, in fact, okay? Between the state vector themselves, and between the entire vector. And this is done all at once, independently of the dimensionality of the vector. So this is why, of course, here we are at the core of why quantum is so powerful. And this is why also it's very appropriate, of course, to make support vector machines and inner product calculation with quantum machines through quantum kernel calculation. So there are two strategies to calculate this inner product. One is the swap test circuit that looks like this one. And this one typically can be so we can, of course, with several shots, estimate the expectation value of this using ancilla qubits. Here, this one, when we measure here at the end, this ancilla qubits, and using control swap gates, which are gates that swap the value of this qubit with this one, depending on the value of the ancilla qubits. There are another also circuits that we can use. Typically, we refer to the compute and compute. This one, we call it also the direct fidelity circuit that we can also use to make those inner product calculation. So remember that for our kernel function, we have to compute all pairwise kernel value on a training set. So to obtain the matrix, we will have all the pairwise xi, xg. And with this matrix, once again, we use this matrix as input into a classical kernel method with the optimization part. And all of this yields what we call the hybrid quantum classical learning pipeline. So even though we are in the quantum SVM, the quantum part here serves through these circuits to make the calculation, to compute the inner product that we need in order to build our kernel matrix function, our kernel matrix. So the two distinct stages here are the one I just explained to you, the gram matrix building and the optimization part to calculate the alpha coefficient. And here it comes, in fact, a flow of quantum SVM, especially for big data when you don't know the distribution of your training sets. Because building this gram matrix, okay, force the QPU to physically cross-compare every single data 2 by 2. And in addition to that, you have to repeat S-time in order to counter your shot noise. So you have a global complexity in terms of resource of quadratically to your training set multiplied to the shot noise. As you know, the shot noise is really to this is used in any case. It will be, of course, is to counter your the qubit measurement fluctuation, and it's of course something that is shared across any I would say any non-deterministic quantum algorithm. So you have also this in addition. The optimization part that does not take place on the quantum computer, as said before, and that also adds to this complexity an additional, not quadratic but cubic optimizer cost. This second part here is what is the part of the what we call the hybrid pipeline. Okay, quantum classical. There is indeed the historical quantum SVM theory that came out in, I think, 2014, and this variant was addressing FTQC, so error-corrected quantum computer, and that would be, this one would be indeed completely quantum, including this second part. So the first part is calculating the inner product on the quantum computer, and the second part is calculating this coefficient through quantum linear algebra. Quantum linear algebra using quantum singular value decomposition or HHL variant to work with not matrices but directly with your density matrices that we talked before, okay, but remaining coherently in our quantum circuit. But today, of course, even in the early FTQC, let's call it like that, coming area, we definitely need to address this hybrid classical quantum pipeline instead. So if we still in this classical hybrid pipeline, since we still depend on the classical optimization, what are the quantum support vector machine advantage? In fact, the advantage are not quantitative for the complexity reason I mentioned just before, but so far we have seen that they could be qualitative in terms of expressivity. There were some major milestones in this quantum support vector machine done by the team of Google Quantum AI in 2021, who did rigorously demonstrated that even though classical kernel, so in classical kernel used in SVM, classical SVM, those one typically work in infinite dimension because they work in the real space. They suffer from what they call prediction limitation that requires exponential amount of training data, and who also suffer from inductive bias like isotropic bias, and therefore being unable to guess the underlying structure of complex data problem. So the quantum SVM equivalent is using, in fact, a much more rich projection into the Hilbert space, thanks to the way we encode the data and the way we use what we call quantum ansatz or quantum circuits to build this phi feature map function that we initially talked about in order to project your data into a much higher dimensional space of the Hilbert space in this case. So that this was a big milestones in advancing, of course, the argument that QSVM, even the hybrid QSVM version and variant, could still be useful to discover patterns that are invisible to classical algorithm, thanks to a more expressivity of the quantum circuits and the QSVM space. But still, we still suffer from the quantitative, the speed up part, okay? So I think this is the last slide with some math, and I'm going fast over it because it's not, this math is not that easy, but I want to just justify the transition from quantum support vector machine to quantum reservoir computing, okay? You remember that in quantum super vector machine, in order to evaluate the similarity between your two states, to know if your data are similar or instead are far away from each other, you were using the quantum kernel function, and typically you were measuring your inner product using the swap test or the compute and compute circuit. And your kernel function was represented through your density matrices. Density matrices is once again an extension of your state function with when you take into account real QPUs, real hardware with noise. So now to bridge with the reservoir readout, you remember at the end of the reservoir was like a fixed circuit, but at the end you read, you make this synthetic observable that you choose to represent your feature vector, and this feature vector will be introduced in your linear regression, into your classical AI rich regression, for instance. When you in fact introduce the density matrix in the operator space that I talked about, the operator space of 2 to the n by 2 to the n complex matrices with the Hilbert-Schmidt inner product. This is the tensor product of n qubits with all the Pauli matrices, and who are typically forming a complete orthonormal basis thanks to this Hilbert-Schmidt inner product with the trace operator. So the density matrix is represented as a linear combination of this orthonormal basis of Pauli multi-Pauli operator. And the way here those classical coefficients are expressed, in fact, those coefficients are exactly the expectation value of quantum observables, the quantum observables that we used as a readout of our quantum reservoir. When you look at these classical coefficients here, what you get is the observable mu of I being here a combination for every qubit of, depending on what you have chosen, of one of the Pauli observable on the corresponding qubit. And when you, let's say, input those classical coefficients in your kernel, in fact, what you get is this linear combination of observables as output. And of course, here we are talking about the complete operation, the complete density operator space. So we will have 4 to the n, of course, basis of Pauli operator if you take into account all the different combination of Pauli operator on every of the n qubits. But what we do, in fact, with the quantum reservoir is choosing a subset of those. We are not going to take, of course, this exponential number of quantum observable. We choose a subset, so it's really a truncation that gives the quantum reservoir computing a quantitative advantage to the QSVM. So instead of, for the global QSVM kernel, we expand to a sum of expectation value, but restricting those expectation value to a subset S of a polynomial size local observable, typically local observable of weight 1 or weight 2 poly string like Zi or Zij. And once again, this is really to justify that we are transitioning to the quantum support vector machine, which is once again a very strong theory of performance to make classification and to make linear regression, into the reservoir, where typically you can consider the readout as a subset of a quantum kernel for the QRC, even though, as you already understand, as you will see, in the reservoir, we don't have to explicitly calculate the kernel matrix. We will do this in a streaming mode. So typically where the quantum support vector machine is afraid of the quadratic complexity, that becomes a problem to address big data, because you will depend on the number of data in your training data set. Here on a quantum reservoir, we are not afraid of the big data. And in addition, we have this quantitative also performance scaling compared to QSVM. So you understand that the QRC does not abandon the power of the quantum kernel, but we make it scalable. We make it scalable for the reason I just explained, in terms of how we gain quantitatively on both the training and also the fact that we are able to handle big data. And we are not limited anymore. I mean, yes, we are limited, but we are limited in a linear time with measuring the observable. And we do this once again by exporting a similar kernel structure, but this one is exported in a classical linear ridge regression, which is extremely easy for current CPU, of course. And all of this with the same expressive landscape that the one that we have by the truncated quantum kernel that we got from choosing these subsets of observable. By the way, this mathematical simplification with the subset is something, by the way, that is also addressed by quantum support vector machine with what we call kernel alignment. But of course, the complexity resource and complexity of the compute still remains. Okay, it doesn't change the problem. It just eventually simplified, but not in terms of complexity. So in QSVM, to summarize, the data size is really a bottleneck. That's why, once again, as I said earlier, we are working on highly expressive pre-processed data to limit, of course, the training resources and costs needed to build this kernel matrix. It scales quadratically on the QPU to calculate, if you remember, the inner product, and cubically on the CPU for the hybrid optimization part. In QRC, we have the same expressive kernel, but the data size only impacts linearly our training being, once again, limited to a classical linear ridge regression. Very, very simple. So now all of this work is we have done in comparing quantum support vector machine and quantum reservoir computing is nice because we understand the limits. We also know that we are based on strong mathematical theory of support vector machine to justify that our reservoir will produce meaningful prediction, meaningful value, and that it is not magic. And when you look at QSVM application, in fact, this gives to quantum reservoir computing paradigm a lots of target benchmark to try to compare use cases and application on how they are being solved in QSVM in order to solve them easier and even with more expressivity with quantum reservoir computing. You have here application of QSVM in network intrusion detection for cyber defense. You have anomaly detection in cybersecurity. All of these are, I didn't find the time to put the reference, but all of these are archived scientific paper that I found related to quantum kernel and a supervised classification method. So we understand the basic mathematical foundation of our quantum reservoir, and we need just a few more remarks about fine-tuning the reservoir. So fine-tuning the reservoir is, in the first place, you remember how we encode the data, how we embed our classical data in quantum states. And so typically we will choose an angle encoding that is done through rotation angle. So if you have here a vector, a real vector of classical data, what we will do here is to use several Pauli natural rotation on every and each individual data. What is nice with this is that this rotation, in fact, will introduce nonlinearity. You will have a lot of cosinus, sinus appearing based on your input data. And of course, by mapping these classical data into the parameters here these are the parameters of your quantum rotation gates, this induces a lot of trigonometric function. And this trigonometric function will capture nonlinear relation into your initial input data space. Of course, you have to ensure that you have a mathematical injectivity, essential to make sure that different values are encoded in distinct quantum states. And you have to take, of course, care about the range that are given here to the quantum rotation gates. Finally, in terms of fine-tuning, the first thing to realize is that thanks to the angle encoding, what you generate, in fact, in your Hilbert space and that you will use as feature for your linear regression are, in fact, Fourier harmonics, naturally Fourier harmonics. Because when you operate quantum rotation, you get, in fact, terms like this. And it's easy to understand that with the binomial factoration, when you compose the different states of the qubits, will generate here a very rich Fourier harmonics in the amplitudes of your density matrix. And this density matrix, once again, is the one that you will sample in your readout. Another way also to fine-tune your quantum reservoir to even have higher degree of harmonics, especially for chaotic systems, who are the highest nonlinear systems, is one way of doing that mathematically is by doing reuploading. Reuploading, in fact, is a technique of injecting exactly the same data. Not for when I say the same data, I mean typically if we are talking about a time series, it's the fixed value of the current time steps. But we do it multiple times within the same circuit, and in between we interleave this with layers of scrambling gates, the ansatz circuits. And the effect of this repeating, re-uploading data is typically to have access to higher harmonics in terms of higher degree of polynomials. And this is something that, of course, can be useful when you consider predicting the future states of a system, and when you imagine decomposing here the future state of your system into a Taylor expansion, you will see, of course, that what you need are the non-linearities that will happen, that will appear with derivatives and higher order derivatives. And of course, these derivatives will depend on the mathematical modeling of your input physical problem. Okay, so of course, depending on this, you will have more or less higher dependencies on this high degree of harmonics. But you can address this by doing re-uploading of the same value. And by the way, since a quantum reservoir also needs what we called a fading memory, well, just talking about that on next slide, you can, of course, it's useful to know that instead of talking about Taylor expansion, you can talk about Volterra series, which are generalization of Taylor expansions, but to nonlinear dynamical system who have memory. And the memory is something that is very useful as a basic, I would say, property to have a quantum reservoir. The basic properties is what we called the echo state property and the fading memory. And those two properties are required to remain your reservoir physically stable and reproducible. This ensures, in fact, that the system gradually forgets its initial starting condition, preventing unmapped saturation of chaotic drift. If you come back to the analogy of the bucket, if your bucket was not fading the amplitude of the ripples after throwing pebbles far initially in your buckets would become a completely uncontrolled chaotic system that you will not be able to drive for a computation. So let's resume a few ideas, a few concepts that we have learned for quantum reservoir computing as an early FTQC approach. QRC does not abandon the power of quantum kernel, but it makes them scalable. Streaming strategy for big data, no problem. QRC can process data sequentially with linear complexity. We can also consider that the QRC is bypassing the explicit numerical simulation. Of course, it is not a physical simulation tool. It's not a pure algorithmic approach where you would fine-tune every gate in order to solve a complex equation. This is definitely useful, but would require not an early FTQC, but a full million qubits FTQC quantum computing, deep circuits and complex oracle structure. So we are more using a QRC in early FTQC approach, as we said earlier, by talking about the possible application, by using the QRC as a complex temporal signal processor. It is also eco-energetic because we don't have to train as QSVM is doing. There is no barren plateau problem like variational quantum circuits, because once again, we don't optimize the ansatz, which is not trained hybridly with a classical optimizer. And all of this makes it definitely eco-energetic compared to other kind of approach. We have this exponential dimensionality, the natural one, of course. If you come back to the comparison I did with the generative AI, who today's biggest model require 10 to the 12 parameters. You are already at 10 to the 15 amplitude parameter when you are using 50 qubits. But of course, for all of this to happen, you must design a structured problem-specific feature map, because what we want to sample at the readout is only, of course, a lower dimensional submanifold of your Hilbert space. You cannot spread, of course, your data randomly in the complete by filling the complete Hilbert space. Otherwise, you will fall into a completely concentration of measure, of unuseful measure, and not being able to predict, of course, anything with your linear regression or classification part at the end, at the output of your reservoir. A few review of scientific paper and experimental proof about quantum reservoir computing. There is a nice article here mentioned at the end of the slide that used the quantum reservoir concept on a model of weather prediction that we called Lorentz 96. Lorentz is the mathematician who invented fractal strange attractor, chaotic strange attractor in 1963, who gave, by the way, this the strange form of a chaotic strange attractor in the form of a butterfly, quite well known. And this Lorentz came back in 96 also with another chaotic model represented here by a coupled nonlinear differential equation, historically of 40, to represent, in fact, the atmospheric circulation at mid-latitude in 1D, but sufficient, in fact, sufficient when here the forcing, external forcing is bigger than 8, to have a very extremely chaotic strain behavior attractor, and typically, once again, characterized by non-integer dimension, which characterize the fractal model. So the idea explained in the article to explore the quantum reservoir computing for this model is to make sure that the reservoir design has, in fact, the same invariant, is characterized by the same invariant of the Lorentz 96 toy model. This toy model is a model that from which you can extract, in fact, invariant that we will call Lyapunov, spectrum and Kaplan-York dimension. Those are the dimension of your strange attractor, non-integer dimension, by the way. And what the article says is that we are designing, in fact, a circuit with a certain number of hyperparameter that we will adapt in addition to other things in the design of your reservoir, including, once again, the encoding part, but also the observables, etc. And making sure that we get the same invariance. And how do we do that? In the article, they compute, in fact, the Jacobian of the QRC and compare it to the one that we extract from our target Lorentz 96 attractor toy model. So it's quite interesting article on the weather prediction, which is, as you understand from this article or from this slide, that is of course a very highly nonlinear chaotic problem, extremely difficult problem. But we are definitely in the domain where I initially explained you that accuracy could bring value. So I definitely recommend this article. Another one from recent one in March this year from ETH Zurich and the IBM team demonstrates that we can successfully break the measure concentration barrier on digital QPU by using, in fact, a non-transverse Hamiltonian. And in this in this non-transverse coupling Hamiltonian, they are using, in fact, the coupling parameter J, H, and B for the longitudinal and transversal field as hyperparameter that they are going to optimize by grid search, like you are doing hyper parameterization in classical AI. But as you will see, what's quite interesting in this article is that they were able to find some universal operational regime where, in fact, after being able to optimize on a Pareto front a small circuit of 6 to 12 qubits, that this one was able to continue to have these generalization capabilities, but on a much larger scale. So if you increase here the number of qubits from 24 to 72, typically they were able to demonstrate that on a very complex benchmark that we call the NARMA benchmark. They were able to conserve a very good score by keeping this by scaling this memory capability of the reservoir once it was optimized, but at a much smaller scale. So this is definitely extremely interesting results. And yeah, increasing the qubit volumes directly extend the effective memory of the horizon of the reservoir, but while preserving the output variability. And once again, the variability of the reservoir is something that is extremely important. It's this variability that allows your linear regression to find easily being able to easily predict your value by a simple linear combination of your feature vector. And the feature vector is characterized by this variability. If it's not, if you don't have this variability, and once again, this happens when you increase the number of qubits, because your Hilbert space becomes so big that you have to make sure that you are that you are focusing on a submanifold of this Hilbert space, and not spreading randomly into this too highly dimensional. When we are talking about 124 qubits, we are talking about 2 to the 124 dimensional Hilbert space, right? So yeah, once again, also yeah, it doesn't. It's what I said about the scalability. I want also to mention to come back to another experiment that we did at QUOBLY to test quickly, let's say, a basic reservoir concept, but mainly on using the new open source framework principles that Marta talked about last week with on the same TerraTech seminar. And with this, in fact, just as a very quick reminder, this principle framework is something that use our native hardware compiler, and that allows you to perform pulse level transpilation and provide noise accurate simulation under our realistic non-Markovian pink noise, which is characterized by the power spectral density of inverse of the frequency to the alpha being 1 when it's the pink noise. And all of this framework can be used, in fact, to start from a cascade circuit, for instance, and come back with, by integrating at the pulse level, the noise model of our quantum computing processor at QUOBLY, come back with the equivalent circuit that represents the noise included. So we did that, and the idea was to do the same kind of benchmark that was used on the IBM paper, which is a benchmark for time series forecasting on what we call NARMA-N. So this NARMA models is a highly non-linear. Sorry for the slide. I realize that it's not in English, but just look at the equation. It's sufficient. You see that, in fact, the time series here depends, of course, on the past value, x of t minus I going from up to the big N value. So highly, let's say, with high past correlation depending on the value of the NARMA N value benchmark, and also with linear dependencies on the new input data, U of t, and past input data. So on this, so you have indeed the equation that is represented here with some value, random initial value for, of course, for as a benchmark, with both the input U of t and the target, depending on the choice of the scalar value alpha, beta, and gamma. Indeed. And then to come back also to the coefficient that was used, yes, sorry, also in French, this one, but to come back to the score that IBM was using here to represent the memory horizon, which is called the R2 score. R2 score is here the coefficient de détermination, and which typically explains how much of the variance in the signal is explained by the reservoir. So when you have typically a 0.7 value, is considered as an excellent value. So here is a real execution of a naive QRC simulated within our QUOBLY spin pulse environment, and without applying any hyperparameter optimization loops or whatever on this simple ansatz circuits, we were able to obtain those kind of R2 value for predicting the NARMA benchmark on 5 qubits. As you understand, there are lots of open question, lots of area of research that still must be done and could be done, and of course the fundamental open question is how to I would say industrialize the process of building an efficient and designing an efficient reservoir. And among those subclass of this design problem, you have, of course, the encoding strategies who best match depending on the given signal class. You have this QSVM QRC migration that I choose to talk about today a little bit more into the details, and including mathematical details. You have also an interesting new algorithm that came out, which is the quantum oracle sketching algorithm, that could also be useful to be used as an encoding, a new encoding strategy, and also how the noise interact with reservoir expressivity, especially in today NISQ area or early FTQC, in the coming early FTQC area. And Nicolas, by the way, is going to also just give a few words about the impact of the noise on some results. But definitely this kind of impact is not exhaustively addressed or studied. At last but not least, I want to recommend, if you're interested by quantum machine learning in general, I can recommend you a book. In fact, the QUOBLY is backed by a stellar scientific advisory committee, and among them you have Min-Sui Sui here, who is a real pioneer in quantum application. He's the director of the quantum computing research in On-High Research Institute in South Korea. And he wrote a book that I don't have on the slide, but I can show you here, which is a gentle introduction to quantum machine learning. I don't know if you can see my book, sorry, like this. Why is it not working? I will put the reference in the slide. But this book is quite recent. It comes from last year, and I find it particularly interesting, especially when you start from basic, I would say, knowledge in quantum machine learning. I would say, not quantum machine learning, but and that's it for me. Thank you for your attention. We are going to continue a few more minutes with some presentation of QRC lab code on Visual Studio with Nicolas. But just before, maybe I can take some question, and also we can do like a 5 minutes breaks for a glass of water or coffee.
Alain, I see there were some questions in the chat. I don't know if you saw them all.
No, sorry. Let me.
Wait, as you want, if you prefer to take a little break before answering.
I will just stop sharing, because with sharing my screen, I don't see, in fact, the chat. That was the problem. Yes, now I can see it. All right. The classical, it's not easy, of course, to come back to. So let's take this first one. I think I answer it, of course, because it was doing in the presentation. But the QRC, of course, do not suffer the Barren plateau. Because typically it is not trained. It is we are not training by any kind of variational optimizer or hybrid code, because it's a fixed. We are talking about fixed quantum circuit ansatz. I don't really get the transition between QSVM and QRC. QSVM is independent in time, while QRC depend on time. QRC is not depending on time. It's treating quantum time series, but in both cases you are inputting value one at a time, depending on if you are handling with time series or static data. QRC use local observables. Why? Because this is, of course, this is linked to the choice of the subset of observable that we want to choose as feature vector, once again, to input then as parameter for our linear regression. So this is why. Could you advise some source for the transition between QSVM and QRC? In fact, to be really honest with you, I didn't find any source from this transition. I would be interested myself. But this transition is something I was looking, digging myself into. About spin pulse library, how many qubits and what depths can you reasonably simulate with it on a laptop? It depends on your laptop. If you have your gamer laptop, you will probably be able to go up to maybe 27 or something like that qubits for QRC, but it's just mainly in terms of having, of course, a lots of VRAM and also, of course, a GPU. That's why I was referring to a gaming laptop, a GPU with a lot of VRAM. QSVM deals with static data, but QRC can deal with dynamic data. Thus, the dynamic data depends on time. The dynamic data depends on time, and indeed, you are entering, in fact, your data before making your readout. You input a sliding window of your temporal data into your quantum reservoir. By inputting, of course, sequentially, this allows you to capture the correlation between the different the data at that different time, because of course when you sequentially enter this and encoding this through quantum embedding, it spreads your value into your Hilbert space. It spreads your value to many different amplitudes of your state vector, and of course those one fades away if you are not working with if you are working with a too large sliding window. You have to make sure that, of course, you have this fading memory in order to exploit your reservoir. Otherwise, you are not. You don't have the main physical property of a good reservoir if you don't have this fading memory. Fading memory, that once again is not really a problem if you use a short sliding window. If you use very large sliding window, you have to handle this by extract the entropy from your circuit by partial tracing through ancilla qubits. So reading in fact your density matrix, not completely, because you don't want to collapse your quantum state vector, but still by extracting some information from it, more or less like a quantum error correction is being done. This choice of observables is arbitrary, right? It's not completely arbitrary. The nice part is that the seminal paper from Fujima and on quantum reservoir computing is that they demonstrated, as I said in the very early slides, that you are able to approximate nonlinear system with only local observables. Once again, you don't need to have the full you need the full basis of Pauli operator, but you can choose. They were referring to weight 1 and weight 2 Pauli operators on a n-qubit tensor product, and the way, of course, you the more, I guess, you add, of course, observable, and the more you build those synthetic observable, the more you will have expressivity and richness to give as input parameter to your linear regression. But the way typically the article from IBM is handling that is that as output of the reservoir, they were operating a quantum singular value decomposition to make sure that they were choosing the eigen mode, let's call it like that, of the reservoir. Typically the singular value mode or singular value vector that are the most representative. So this of course induced some post-processing on the readout. But the nice thing is that this is something that they did at the smaller scale and keeping the choice after scaling to 124 qubits. If your reservoir circuit commutes with some group, do you have to choose your observable in such a manner as to respect the symmetry if you want to learn data that has some symmetry? What definitely, yes, what I can say about that is what's important is that you keep the mathematical symmetry of your problem with the choice of your encoding is not a problem, but with the choice of your typically ansatz circuits. Since we are talking about unitary operation, in fact, what's important is to have what we call the equivariant circuit that indeed that makes sure that if you apply as you said, some group symmetry to your input data, that you can do, that there is some unitary operation equivalent in your feature space that can remain invariant with this symmetry operation, but in the feature space. And this is definitely not easy to neither to prove or to design, I guess. There are a few articles that train input data classically, and they put the last layer into quantum states, then reservoir layers, while others encode directly the untrained input data into quantum states, then use reservoir layer. In your opinion, do we need to train data before QRC? You definitely don't need to train data before QRC to answer this last question in the first place. What you can do, of course, is the PCA analysis to reduce the dimensionality. To reduce dimensionality of your input classical data. This is a good idea. You can also reduce the dimensionality by adding encoder, auto-encoder quantum circuit. That is also an option, but I guess less interesting because you lose the physical interpretation maybe of the input data. And to come back to maybe your initial question, when you say that there are some reservoir that indeed, if I understand right, re-encode. Let me reread your question. They put the last layer into quantum states, then reservoir layer. Yes, I guess you are referring to the fact that some reservoir design strategies is to do some re-uploading, the concept that I talked about, but instead of re-uploading the input data, they re-upload the classical readout, and this is an additional strategy that I cannot compare, but that is indeed used in some article. And I think that was the last question so far. You can come up with other question maybe after the 5-minute pause, and we will continue then with Nicolas. So see you in 5 minutes.
Hello, everybody.
Hello, Nicolas.
Hello. So I'm Nicolas, and I'm an intern here at QUOBLY. And we're gonna go right into it, I guess. So what I'm gonna present is really just a simple notebook that's sort of gonna reiterate a few of the things that Alain has gone through. He's gone through a lot of good information, so hopefully it'll be a good resume of all of that. Feel free to ask questions in the chat like before. And if Alain, you could also reply to them in the chat as well if you want. And so, yeah, I'm just going to start by sharing the actual notebook. So it's made with QRC Lab, which Alain has mentioned a few times, and it's a really good GitLab repository with a lot of good tools for quantum reservoir computing. And on top of that, we use our own package for simulating and designing quantum circuits spin pulse that Alain has also gone over. So I won't go through them again, and you've seen it in the presentation last week also. A lot of great stuff has come from it though. So yeah, again, for the QRC stuff, I won't go over the specifics or the details again. I'm just going to show you how we use it and how we can apply it to simple problems to start off with. So here it begins with the classic Python imports. And for our first example, I'm going to show you this short-term memory task, which the goal of it is to give an input set, time series set. What is the previous data point that was uploaded? So here, for example, we have our input set, which is the blue lines. And for each input, you have your target, which as you can see is going to be just delayed by one step. So it's a very simple task, a very simple toy example that runs really quickly because there's not much to train on it. It's very easy. Again, for encoding, I'm not going to go over it, but just to give you a quick look at, or a quick reminder of what it looks like. This is just the regular angle embedding to where we directly take our data and put it onto the angle of rotation of a quantum gate. In the actual hardware, it translates to the amplitude or the shape of the pulse that's sent onto the qubit. So it's, in this case, it's a one-to-one encoding. However, just to give you a bit more flavor, we're going to be using the re-uploading encoder, which is, it takes the angle encoder and it repeats it multiple times and it adds random gates in between to add a bit more expressivity into the actual encoding itself. So this is what the encoding looks like. We get the classical data onto the quantum computer. Now for the actual building of the reservoir, we use a random-ish rotation reservoir that includes a few entangling gates and then just some regular rotation gates on one qubit. And we also build up a reservoir with a few back-end options, such as the number of shots. And there's also the amount of times that the data is re-uploaded. I won't go into the specifics of that, but it's something that's also done in regular machine learning, where you re-upload your data for more expressivity. So now that we've encoded our data and we've built our reservoir, we can actually run our circuit a bunch of times and then train our output layer on that. And then again, the training is really only dependent on the results of the measurements. And we don't actually train the circuit, or the quantum circuit, I mean. We only train on the outputs. And as Alain stated, we trained on a regression model. So then again, there's a lot of things to tweak and a lot of hyperparameters that you could tweak on it, similar to AI, and there's a lot to play on here. So here I made a function just to encapsulate it all, and I've got a few test runs here to show you. So yeah. So when we run and train it, we get a few different results, and we get some training results on our output layer that we can then use to predict on a whole new batch of input data. And as you can see, this is just a standard QRC with no spin pulse at the moment. And as you can see, we get a a pretty decent R2 or I squared of 0.56. So now we can move on to integrating it with the spin pulse library. So then again, I won't go over what you've seen last week, but a quick reminder, this is transpilation. So when we write a circuit, we need to transpile it so that we can actually run it on the hardware, because the hardware always has its own set of constraints. So it can only run certain gates, and it can only run certain qubits together. So that's another interesting challenge that also has its own set of algorithms that you can use, and there are a few on spin pulse as well. So when we do this, we add in all the information on the hardware that we're going to run it on. So we have a few basic parameters here that determine the gate times, the Z gates and the X gates, and then a whole bunch of noise parameters and a few like the T2 times and the TJ times. So then once all those are set in, we can actually transpile our original circuit onto our hardware restrictions using the gate transpile function. And then we can take that back if we want to into another regular circuit using the from circuit function. And then we can also extract the duration of our circuit so that it gives us an estimate of how long we have to run it and so on. So this is what it looks like, the actual reservoir circuit. And now we will move on to building the circuit with spin pulse in mind. So again, I'm building an encoder, and then I'm building a reservoir. And then for the observables, it's the same observables as before, and it's just a Z gate on each qubit independently. And as you saw, we can still get some pretty good results for this simple example. And yeah, so we build our simulator based on these things. And we also here, when we built the reservoir, we took in the transpiled circuit that we just looked at. So now we run and train exactly the same way that we did before. And as you can see, we got pretty good results and actually better than before. So yeah, so it's fairly interesting to see how, as we transpiled it onto the spin pulse computer, and with all the restrictions that come with it, we do get a better result. So that's just to show that there's so many different parameters to tweak and to play with that can really have a big impact on the result of your reservoir. And now that we've seen this toy example, and it runs fairly quickly because it's fairly simple, we can move on to the NARMA problem. And this one, as Alain showed, is more challenging. It's a lot of nonlinearity and deeper memory requirements. So same thing with the imports. And here we're doing NARMA 5, which is a very, very basic version of NARMA. And this is what it looks like. So you have your inputs, and then you have a lot more of this irregular output data based on the function that you saw from Alain earlier. So it's the same thing. We run and train this reservoir, and then this first one again is just the standard implementation, so without spin pulse. And when we run and train it, we get this result. So it's a pretty bad result. However, what we can do is we can try tweaking it. Since this is a more complex problem, we can add more qubits, for example. So here I just added 2 qubits. We went from 3 qubits to 5 qubits. So it's not a huge jump. It's pretty easy to simulate still. And then same thing. So another thing too is that you'll notice for these first few inputs, the target data is set to 0. And that's because at the order 5, in our case, we only start computing the values after the 5th value. So what we do is that we add a washout. So basically, we ignore the first few parameters and we give the model time to learn and memorize the overall characteristics of our input signal. And this washout is something that's also used fairly commonly in any reservoir scenario. So when we add this washout, as you can see, we still have a pretty bad result. And that's due to the fact that we need to change more parameters, especially the scaling parameter. It can change the result a lot. And now going back to actually implementing with QUOBLY, it's the same input problem, so the same data, and we added all our nose parameters of our computer, and then we transpiled the circuit. And as you can see, when we run it with the re-uploading encoder and then the reservoir, we put that all together in the same observables. When we run it, we actually do get a significantly better R-squared result. So this just goes to show that, again, there's a lot of parameters to play with and a lot to work on here. So yeah, so we also have just an example of the many parameters that there are. You can work on the encodings. As Alain shown, there's the basic angle encoding, and then there's a re-uploading encoding. Then you can look at different alpha values for the readout model. I won't go into exactly what that does, but there's also the linear regression model type that you can tweak. You can tweak the observables that you choose, and a whole bunch of other stuff. So yeah, that's just a quick demo of what I had to show. Thank you for your time. Yeah.
You had a question about how many reservoir layers that you have used.
Oh yeah, so right now I'm only using 2 layers. And that's for the readout memory task and the NARMA task. So very, very small circuits, and we still get pretty good results. Obviously, the more layers you use, the longer it takes to simulate. So yeah. Any advice about the number of reservoir layers? So good question. And it's a difficult question for me to answer because at the moment, the approach would be to start small and then increase as you go to see how many layers you can go until you reach a certain wall of simulation. However, you can do a lot of layers, but then the issue becomes similar to an issue of overfitting actually, where it might be too complex and then you add in by adding many layers, you sort of create more chaos. So then again, it's another trade-off of keeping your information pure, but also allowing it to mix well into the reservoir. There is a lot of information on actually finding the right size of reservoir in the papers that I would definitely encourage you to read.
And also the goal of Nicolas was also to understand the impact of the noise of QUOBLY's quantum processor on these circuits. So of course the number of layers here is that we are interested in is also related to the kind of noise that the kind of noise model that we have, and definitely, of course, the noise at some point will destroy the reservoir. Maybe it could be, as I said in my slide, we don't know the explanation that from maybe some small noise could be useful, even though we don't understand why. But certainly in a large expansion with many layers, it won't be useful for sure. There are many ways. I mean, the question is, if I understand well, there are many ways to make measurement for QRC. I would say, there are many measurements for any quantum algorithm on QPUs. Yeah, this is maybe a too generic question to answer. Sorry. I think we don't have any more question, Marie, and I thank you. We thank you for your attention, and thank you for all the many and great questions. It means that you were following, and the question were definitely right on spot of the QRC.
Yeah, thank you, Alain. Thank you, Nicolas, for this great presentation. Very happy to have QUOBLY with us, and hope that we'll be doing other things together soon. It's always a pleasure. And thank you very much for attending. There will be the replays of last week and today available on our YouTube channel very soon. I'll put the link on the chat if you need. And we'll be, of course, organizing other Quantum in Practice sessions very soon. So stay linked to our YouTube channel or LinkedIn to have the next agenda incoming. So thank you very much, and have a great end of the day, and see you soon. Bye.
Bye. Thank you.
Thank you for your time. Bye.